Gravitational lensing, nature's telescope. Gravitational lensing is a phenomenon where the gravitational field of a massive object, such as a galaxy or galaxy cluster, bends and magnifies the light from a background source. This process is predicted by Einstein's general theory of relativity, which describes how massive objects distort space-time, bending the paths of light rays. When a foreground object, lens, aligns with a distant background galaxy, it acts as a cosmic magnifying glass, amplifying and revealing faint galaxies that would otherwise be invisible. The Hubble Space Telescope has captured images of distant galaxies magnified by gravitational lensing, such as the iconic Einstein ring, where the light from a distant galaxy is warped into a circular arc by a massive foreground galaxy. Gravitational lensing is like looking through a wine glass. The curved glass bends and magnifies the image of objects on the other side, making hidden details more visible. 2. The physics of light bending in spacetime. Massive objects create wells in the fabric of spacetime, causing light to follow curved paths. The bending angle of light is proportional to the mass of the lens and inversely related to the distance between the lens, the observer, and the source. The degree of light bending reveals the lens's mass distribution and uncovers distant objects by focusing their light toward Earth. In the Abell 1689 galaxy cluster, gravitational lensing magnifies and distorts the light from galaxies billions of light years away, allowing astronomers to study their properties. It's like placing a marble on a stretched rubber sheet. The marble creates a dip, and rolling balls, light rays, curve around it, following the sheet's distorted contours. 3. Magnifying distant and hidden galaxies. Gravitational lensing can magnify distant galaxies by factors of 10 to 100 times, making faint galaxies detectable. This magnification also increases the resolution, allowing astronomers to study the structure, star formation, and chemical composition of galaxies from the early universe. Without lensing, these galaxies would remain hidden due to their immense distance and faint brightness. The galaxy MAX 1149 JD1, one of the most distant known galaxies, was discovered thanks to gravitational lensing by the MAX 1149 galaxy cluster. The lensing effect amplified its light, revealing details about the galaxy's formation just 500 million years after the Big Bang. It's like using binoculars to view a tiny bird in the distance. The magnification makes details visible that would otherwise be missed by the naked eye. When the source, lens, and observer align perfectly, gravitational lensing creates an Einstein ring, a circular halo of light. Partial alignments produce arcs or multiple images of the same background object. These distortions are key to identifying hidden galaxies, as they provide clues about the lensing mass and the properties of the background source. Example: the Einstein cross Q223730, a quasar lensed by a foreground galaxy, appears as 4 distinct images of the same source arranged in a cross-like pattern. Analogy: gravitational lensing is like seeing the reflection of a streetlight in a bubble. Depending on your perspective, the light might appear as a ring, arcs, or multiple reflections. Gravitational lensing not only reveals hidden galaxies, but also maps the invisible dark matter in the lensing foreground. The distortion patterns in lensed light trace the gravitational influence of dark matter, which does not emit or absorb light. Example: the Bullet Cluster, 1E0657-56, is a famous case where gravitational lensing revealed a separation between visible matter, hot gas, and dark matter, providing direct evidence for the existence of dark matter. Analogy: it's like using the ripples in a pond to infer the shape and size of an object submerged underwater that you cannot see directly. Gravitational lensing allows astronomers to study galaxies from the early universe, shedding light on the formation of stars, galaxies, and the first elements. By analyzing lensed galaxies, researchers gain insights into the physical conditions during the universe's infancy, such as the reionization epoch. Example: the Hubble Frontier Fields program used gravitational lensing to discover some of the most distant galaxies ever observed, dating back to less than 1 billion years after the Big Bang. Analogy: it's like using an ancient cracked mirror to catch glimpses of a city's distant history. The distortions still reveal valuable details about its past. Strong lensing produces dramatic distortions like rings and arcs, often revealing hidden galaxies in detail. Weak lensing subtly distorts background galaxies, providing statistical data about the mass distribution of the lens. Both methods are complementary, with strong lensing unveiling individual galaxies and weak lensing mapping large-scale cosmic structures. Weak lensing studies of the cosmic microwave background reveal the distribution of dark matter across the universe, while strong lensing of the galaxy cluster Abell 370 uncovered multiple magnified images of a distant galaxy. Strong lensing is like using a magnifying glass to inspect a bug, while weak lensing is like noticing a slight blur in a photo that reveals the presence of subtle distortions. Interpreting gravitational lensing requires precise modeling of the lensing mass distribution and alignment geometry. Small uncertainties in lens mass or distance can lead to errors in estimating the magnified source's properties. Identifying lensed galaxies amidst other cosmic objects requires advanced observational tools and computational techniques. Simulations using supercomputers help refine models of galaxy cluster lenses, allowing astronomers to disentangle the light from overlapping objects and correct for distortions. It's like piecing together a jigsaw puzzle where some pieces are warped. Accurate modeling is crucial to reconstruct the original image. Telescopes equipped with adaptive optics, high-resolution imaging, and spectroscopy are essential for studying gravitational lensing. Instruments like the James Webb Space Telescope, JWST, provide deeper and more detailed observations of lensed galaxies, pushing the boundaries of our understanding of the universe's structure and evolution. JWST recently captured unprecedented details of a strongly lensed galaxy, revealing its star-forming regions and chemical composition at a time when the universe was only a few 100 million years old. It's like upgrading from a blurry telescope to a high-definition camera, allowing you to see distant objects with remarkable clarity. Gravitational lensing is a powerful tool for unlocking the universe's secrets. By magnifying hidden galaxies and revealing their structures, it provides a direct window into the past, enabling studies of cosmic evolution, dark matter, and the early universe. The combination of advanced technology and theoretical models continues to expand our knowledge of the cosmos, showing that even light can be bent to reveal hidden truths. The discovery of the sunburst arc, a galaxy lensed into multiple images by a foreground cluster, revealed regions of